Welcome back, ladies and gentlemen. As promised, in this video we're looking at another example dealing with impulse and momentum. And this one's all about Kobe. Basketball example here. So some basic stats. We know that, well, I did some quick research anyway, that Kobe's weight, at least as listed on the website I found, was 205 pounds. And he had a vertical leap listed at 38 inches. Very remarkable. I mean, this is a big vertical leap. Not the record, but quite impressive. Now, here's the deal. I'm going to be asking to find out one kind of impressive figure, and we'll have to get there in a bit of a roundabout way. But the ultimate question I want to know is, in order to achieve this vertical leap of 38 inches, then how hard must Kobe push on the floor to achieve that vertical leap? This is the goal, the ultimate physics question I want to ask, and I cannot just jump right in. I don't have a single equation that'll give me just that. So there's other things I must do. Now, first, recognize right away that these units are terrible. Pounds and inches, oh my goodness. So I'm going to convert these right away. I do a simple calculation. I look at some conversion, and I realize that 205 pounds is equivalent to almost exactly 93 kilograms. And that 38 inches is equal to 0.965 meters. So that's better for me. Give me some units that I can properly work with in the equations with the tools that I've got. So to get to how hard must Kobe push on the floor, that's a force. Okay. But, well, first things first. We have a vertical leap. We have a vertical distance achieved. And once Kobe leaves the floor, once he's no longer touching the floor, well, he can't help himself anymore. He is on his way up. And so it's an initial velocity that gets him to this vertical height. And at that maximum, at that highest point, his velocity becomes zero for just a moment. So we need to find an initial velocity that's going to get him to this height. So initial velocity in the y direction is going to be the first thing we have to do. And in order to do this, we go back to our big five. So here's our thinking, and one of our big five equations equates a final velocity to an initial velocity. Those two values are squared. And plus acceleration, 2 times acceleration times our change in position, right? This gets modified just slightly because our rate of acceleration is going to be g, and it will be in the downward direction, but our initial velocity will be in the upward direction. And our change in y, well, it's just going to be from 0 to whatever our height is. So that's just going to be this value right here, right? And I have to solve for the initial velocity. That's what I want to find first here. So initial velocity in this case. And after some rearranging of this equation, and final velocity is 0 at the highest point. That simplifies, makes it nice for me. I get the basic equation of 2 times rate of acceleration times that height that Kobe achieves. So I can plug some numbers in, and I get a value of 4.35 meters per second. This is the speed with which Kobe will leave the ground when he makes this leap to get to this height. All right, so this is kind of like a what you call a preliminary step, if you will. So I'm going to highlight this as being an important value that I need to use. All right. So with an initial velocity, all right, so I also have, you would think I have a final, and the final would be at the top. Well, here's the deal. Kobe is not interacting with any object, well, other than Earth gravitationally, not physically in contact with any object while he's in the air. So the velocity he has at this highest point is kind of irrelevant to me now. I want to know how hard he must push on the floor. He must be in contact with the floor to do this. And so this velocity at the top is sort of irrelevant to me anymore. Instead, I need to realize that during the leap, the act of leaping occurs when he starts to push and begins when he starts to push and ends when his feet leave the floor. And that's it. That's the act of leaping. And anything else that happens, any travel to get up to this highest point, is not really the act of leaping. He's just a projectile at that point. So, at least according to a physicist, right? He's just moving according to the laws of kinematics and Newton's laws. But he's not leaping anymore while he's traveling upward to this height. The act of leaping took place only while he was in contact with the floor. So we have this velocity with which he leaves the floor. Awesome. Well, this is now sort of like a final velocity of the leap. And that's our 4.35 meters per second. And the reason we're looking at this is because, well, he has to get this velocity somehow because he's starting from rest. His initial velocity of the leap is 0. And this is real important to recognize because we now can define a change in velocity. And with a change in velocity and a mass, really we called it weight initially, but we have his mass. Now we're talking about momentum and changing momentum and so on, right? So it's important to recognize that we're not concerned with the trip up to this highest point anymore. We're concerned only with creating this trip up with the act of leaping while he's in contact with the floor. There is a change of velocity while he's in contact, and we go from 0 to 4.35 meters per second. Then he leaves the floor and continues on his way up. Cool. So now I'm going to want to find the impulse that really is creating this leap for Kobe, right? So this is equivalent to, let me just use an equal sign, a change in momentum for Kobe. And this is going to be equal to a mass times a change in velocity for Kobe. And now I can plug some values in, right? I mean, it's easy to find the change. Final minus initial. So we have final of 4.35 minus initial 0. There we go. And I know his mass. It's 93 kilograms, 93.0. So left off the 0.0, sorry. And we have a change in velocity of 4.35 meters per second. So we have an impulse. We have this value, 405. Our units are kilogram meters per second. Okay, so this is kind of like again an intermediate step, right? And so I'll highlight that as being an important value, and that is the impulse that caused Kobe to get enough momentum to experience a change in his momentum to get him to leap off the floor. All right. So now the next step, really, well, going from an impulse to an average force, because I ultimately, if you recall, I need a force, I need a push, right? I have to get there to forces. To go from an impulse to a force, I need to also have a time interval, because this is our relationship here, or really this is the definition of impulse. Here's the impulse momentum relationship. Here's our definition of what impulse is: average force multiplied by a time interval. So it is that time interval that I will need. Well, while he's pushing, he's not going to spend a long time pushing. He's not going to try to spend 5 seconds, 10 seconds doing this. He could push as long as he wants. The problem is a longer push is not going to give us a larger impulse. A longer push is simply going to decrease the force. And in fact, it's very counterproductive. So he's going to do this very quickly, is my point. And it might be on the order of, get the pen to work here, less than a third of a second. Okay. It's going to happen real fast. It's if you get into the study of muscles and how they function and muscular contraction, basically the study of kinesiology a little bit, or maybe biomechanics, muscle contractions where you want a lot of power generated, they have to happen quickly. Anyway, that's kind of off topic. So we know that we're looking for the average force. And we know that the average force in this relationship is going to be the impulse divided by that time interval. So we had an impulse of 405 kilogram meters per second, and we're dividing by a time interval of 0.30 seconds. And so we can see an average force here that turns out to be 1,350 newtons. Okay. So again, here we are. We have an average force, and I'm going to highlight that as being kind of an important value for us. I haven't yet said whether this answers the question, the initial question, right? How hard must Kobe push on the floor? Well, what I have here is the average force that's acting on Kobe during the push, during the leap. Not the same thing as Kobe's push against the floor. You'll see that momentarily. Check out this value, though. Holy cow. Okay, so this is a lot. This is different than Kobe's weight, right? We found Kobe's mass from his weight in pounds. We had an equivalency there. And you would think, well, okay, maybe Kobe's actual weight is going to be involved here somehow. And it turns out that it is. So this is the force required to change Kobe's momentum, not the net force acting on Kobe. And that's going to be real important to see. And so maybe it can be very instructive to sort of see what's going on visually. Well, if he's just standing there before he starts to leap, he's just standing. He has a weight pulling down. His weight is just mg. And he has a force pushing him up. And this is a normal force, right? But here's the deal. How hard is Kobe pushing on? Oh, sorry. Those were meant to be the same length. This one's a little too long, right? Or this one's a little too short. So how hard is Kobe pushing on the floor in this situation where he's just standing? Well, Newton's third law says if there's a normal force pushing up on him this large, and it's equal to mg, then this is the floor pushing on Kobe. Therefore, there is a force of Kobe pushing on the floor that is going to be equal to that. That's how hard Kobe is pushing on the floor while he's standing. Newton's third law, action, reaction. But what about during the leap? When he's leaping, Okay, another free body diagram, right? So his weight is a constant value. This downward force. That's still mg. But here's the deal. We know that the upward force, okay, the total force that's acting on Kobe. Maybe I shouldn't say total force. Well, yeah, I can say total force. So we know that this upward force has to produce an acceleration in Kobe. This has to be larger than his weight down, right? Because this much of it, about here, is going to end up getting canceled by the weight. And that downward force would get canceled out as well. And what you have left, this guy, is the leftover force causing an acceleration. All right. Well, this total force, if you think about what's happening, this total amount of force right there. Remember, this is a force of acting on Kobe. This is not what he's producing, but this is acting on Kobe, pushing up, and this is caused by the floor. Okay, so it's really the floor that pushes him up. Well, why is that? Well, because he pushes down on the floor. Action, reaction. So this arrow right here is a normal force. The whole thing is the normal force of the floor. And this is a force acting on Kobe, and it comes from the force that Kobe exerts on the floor. Those two are equal. So the force with which Kobe pushes on the floor is equal to this normal force that is pushing up on Kobe. Again, Newton's third law. But what is this whole value here? So what we have is the leftover right here, which is not canceled out. It turns out that is the average force that we found in our previous calculation. I just had it. Oh, sorry. Oh my goodness, my brain. It's right here on the same page, and I'm looking for a different piece of paper. So this average force, that is this amount that's uncanceled. This is the force that's producing the change in his momentum. That is creating this impulse acting on Kobe. Sorry about that. It's right here in front of us. Okay, but this normal force pushing up is partly due to that, and partly due to more force, which has to cancel mg. So I'm going to be able to say that it's the average force plus mg. And look where we're able to see that the force with which Kobe pushes is equal to the sum of this average force, which changes his momentum, and his weight. And he does have to push harder than this. He's already pushing down with an amount equal to his weight, and he has to push above and beyond this amount in order to change his momentum to create this leap. So what does this look like? All right, so let's actually do this calculation. We have force of Kobe equals the average force that changes his momentum plus mg, right? And we already found that average force. That was 1350 newtons. Kobe's mass was 93.0 kilograms. And G, well, that's our standard 9.81 meters per second squared. So how hard must Kobe push on the floor in order to create this vertical leap of 38 inches? It's pretty cool. He has to push with 2,260 newtons. And we have just found the answer to our question, ladies and gentlemen. That was the original question. How hard must Kobe push on the floor to create this vertical leap of 38 inches? How about that? Took us a couple steps, a couple intermediate steps, but we got it. But this is wild. Holy cow. He is pushing down the floor with a force of over 500 pounds. He doesn't weigh near that much. He weighs two-fifths of that. He weighs 40% of that. He's got to be quite strong, but more than that, as you saw with the time interval being very small, he has to be able to generate this force in a very, very short period of time. Large force and short period of time are combining here to sort of lead to this impulse that is changing his momentum. Pretty wild stuff, pretty cool stuff. All right, that's it for this example. Thank you for watching. If you've got questions, feel free to shoot me an email or go ahead and ask next time you see me. Thank you for watching. I'll catch you next time.